Right, good afternoon, everyone. For those of you who don't know me, my name is Devin van der Walt. So Africa is a dangerous place, especially for the poor animals. And the project I'm currently working on concerns these guys, the great white sharks. And we're trying to help researchers track these magnificent animals and follow them to see, to count their population and see how their habitat and so forth. Recently I had the privilege of visiting some of them in their natural habitat. So, I apologize, the camera is a little bit unsteady, but I was at the time as well. So I don't know if you can see the shark swimming by. I remember it very vividly, at least. There's a second shot, went down again. Yeah, so this guy's about 4 meters long, and just after this, he jumped out of the water, bumped into the cage right next to my knee. Terrifying, but also beautiful. And we have a responsibility to save these animals because their biggest enemy is the human. And we've been very successful at eradicating them. So what we do is we've got guys taking photographs of these on the sea. They give us the photos, and we detect the edges. The edges of the fins are like fingerprints. We do matching on that, and then we can tell them which individuals they saw. So we do generate some kind of comparison matrix and get the maximum out of that. Then we provide them with a graphical user interface so they can match up the sharks in a user-friendly way. The other project that I'll be working on next week is with the Natural History Museum. They've got 150,000 trays of insects that they need to digitize and isolate. So we're writing a graphical user interface for them to automatically segment this image and extract all the insects so they can label it and index it and database and put it in a database. So yeah, I don't know if I've got enough time to show you, but I can run the script. So if just using scikit image underneath the hood, automatically segment the image. It's not a perfect segmentation, it's too hard. The wings overlap at certain stages. So we do the best that we can, and then we just provide them with a very easy to use interface to manipulate the results. So they get a set of tiles out, and those tiles they can then manipulate like that. All right, thank you.
Hi everyone, my name is Zaid, and I'm from Oxford, but I'm here today to talk about LibDyned, which is one of the Continuum Analytics projects, which is a C++ dynamic ND array library with Python exposure. So this is essentially Numpy, but rebuilt in C++. And there are some reasons to do that, and I'll talk about that in a sec. So it's a C++ library for dynamic multi-dimensional arrays. It is part of the Blaze project. It is inspired by Numpy, but tries to address some of its obstacles. So why Dyned? Well, Numpy is great, but ... I mean, there are lots of reasons and things that one might want in Numpy that simply aren't there. For instance, in some cases, you might want variable size dimensions. So if Numpy, if you use fancy indexing, sometimes you get a flat array returned. But that doesn't need to be the case. One could have a dimension with a variable size. You might, I think a lot of people want CUDA and OpenCL support. There's no reason, I mean, there are solutions like PyCUDA and PyOpenCL, but there's no reason why we should have two different objects for an array. Why not just have one with memory located in different places? We might want more flexible data types in Numpy. So for instance, we might want pointer types or variable length strings, things like tuples and structs. I know there is some form of that in Numpy right now, but it's not quite the same. And also, we don't necessarily want to be bound to Python. Python's a wonderful language, but why, for instance, at this conference, there's been lots of talk about Julia. Why do we want to restrict ourselves completely to Python? Why not have something which can be bound to different languages, like an object written in C++? So a dined array, at a very quick glance, is a data shape, which is a generalization of NumPy's d-type and shape combined together. It's got some metadata, so this would say, for instance, the strides and whether or not you're in CPU or GPU memory, and then it has the data itself. And things that are available now are, we have a rich library of data types, so this is, I think, roughly what NumPy has currently, plus a little bit more. You can already do things, various different kinds of computing, like you can do element-wise evaluation of nearly arbitrary C++ functions. And we have reductions and neighborhood reductions on deck, which will be in very soon. Variable size dimensions is something that actually works now. And we also have preliminary GPU support. In particular, you can have multi-dimensional arrays on the GPU and slice them arbitrarily, although that's still preliminary. So just to wrap up, I think I'm not associated with Continuum at all, but I've somehow found myself being the second largest contributor to libdint. And the largest contributor is Mark Wiebe, and he is really the mastermind behind this, and he's been working on it for quite a long time. So I just want to give him credit where it's due. And of course, Continuum, because this is their project.
Hi, everybody. So I have a poster about this already. So you're welcome to see more about this. The idea is shapes, boundaries, regions in images, and other data, say tomographic data, other forms of indirect data. Now, the specific problem of image segmentation, you want to extract objects, their boundaries themselves in the images, so the output could be like this, especially the red curves, which I'm interested in. The disclaimer, a lot of people interested in image segmentation. There's no perfect, universally perfect algorithm. So whenever you have an application, put the specifics into your solution approach. This is to be said. So my particular approach, trying to find the boundaries in an infinitely large space of possible boundaries, curves like this. And the approach, which is a popular and very powerful approach in image processing, is energy minimization. The curve itself, or surfaces in 3D, are the variables. You try to find the curves that optimize a given segmentation energy. And these are designed depending on the application. And I do have implementations of some very good ones. So the way it works, you start with some initial guesses for the boundaries, and then you iteratively deform them in a way minimizing their energies gradually. And it happens that the final configurations are the lowest energy configurations. And there is a lot of flexibility and opportunities related to this, but this is how the algorithm works. It's quite far from straightforward to implement it, and I have the code that I'll be releasing soon. For those interested, you can turn these into meshes for physical simulations or to summarize the image, because instead of 3 million pixels, you could have 30,000. Just to contrast with other possible segmentation applications, if you do a pixel labeling approach, you can get lots of stray pixels like you see in the upper picture. But if you concentrate on the boundaries, you can get nicely decomposed segmentations like this. So another example of thresholding in this situation, and you can see the stray pixels or mislabeled pixels. But if you go with the curve evolution approach, trying to identify the boundaries, you can get very nice boundaries like this, and some triangulations for those interested. Here's another example of thresholding segmentation and the boundaries resulting meshes. Other work that's in progress, shape analysis. You can compare vectors of numbers and quantify them, do data mining on them, but if you have shapes as your points of interest, your data consists of shapes, it's not straightforward how to do this, and the math is pretty involved. So you can do this with our approach and 3D, and so just email me for the code.
Hi everyone, my name is Max. I'm from the University of Southampton, where I'm doing my PhD, but I'd like to talk about a tool which is actually not mine. It's called Sumatra, and I found it really useful in my work, and I think it's worth for more people knowing about it. It basically helps you to keep track of your scientific computations, and so for parameter sweeps and just generally stuff like that. These are the guys, basically Andrew Davison's the main author. He deserves all the credit. I'm just a user and a big fan because it's made my life a lot easier. Just as a disclaimer, Sumatra is the only tool I've tried so far. For keeping track of simulations, there's apparently a lot of tools. This is from Zachary Trout's talk last year. I haven't tried any of them. Sumatra was the first one I tried, and I happily stuck with it. Basically because it's minimally invasive. It requires almost no change to your code, but it helps you keep track of all the simulation runs that you do. It doesn't impose a special workflow, which I find really useful, and just does a good job and stays out of your way. Will it be useful for you? Basically, if you run more than a handful of simulations, if you need to keep track of parameters, like do parameter sweeps or multiple analyses, or just generally care about reproducibility, I'd say give it a try. It's really nicely done and very well-written code as well. So how does it work? Basically, if you have a script that helps you conquer the world, if you just call it with Python, you just say Python script name. With Sumatra, you just tell it, you basically run the script through Sumatra. You tell it the executable is Python, the script main script -m is conquerworld.py, and it just runs it. And before it does that, it tracks the dependencies. It goes through the libraries, tracks their versions, it tracks your environment, and afterwards it keeps track of all the outcomes and the files that you generated. If you configure it, basically all you need to say is then SMT run, and it knows about your script and the executable. So as a simple example, I'd like to showcase one that uses the plot from Stephen Johnson's talk. I found the plot really nice. So here we have a little 2-parameter function which we plot, and if you do that with different values of alpha and beta, you just get different kinds of plot. And just imagine that's a very long-running simulations with, say, 4 or 5 parameters, and you need to do a sweep and need to keep track of that. And most people use sophisticated naming schemes, but it just gets really awkward and complicated. So what you do with Sumatra is basically you separate out the parameters into a separate file, just like here. This can actually be more complicated. Oh, sorry. Can be YAML or JSON format, but can be as simple as this. Then you write your main script, which is basically exactly the same script at the bottom, except alpha and beta are taken from the parameter structure, which we take from a file name that we pass in, and we use Sumatra to build that. And I also change into a separate data structure, which is given by a label that Sumatra assigns to this run, so I can keep all the outputs separate. And then I basically run it by passing that in. I can actually change the parameter values from the command line. Fair enough, I don't have any time to showcase there. Just to say there is a web interface which is extremely useful, so it keeps track of everything and shows you everything about your simulations. I'll stop here, but do ask me if you're interested, because it's really useful. Thanks.
Hello, everyone. Well, that'll do. How do I go through it? Okay. You know that I wrote the book. When I was talking to a colleague in the office a few weeks, or a month ago now, he kept on running out of RAM on his 6-gigabyte laptop, and he was asking me how he optimized his code in IPython to deal with it. And I said, hey, I've written a book. You should read the chapter. Then I realized that he needed something lighter and easier rather than the chapter that treats the slightly more formal process of using Fabian's memory profiler to ask a question and understand how much RAM is being used. So I hooked into Fabian's tool in IPython with a hook. So before and after every command, it will sample the memory that's been used, so that when you use 76 meg of RAM, it reports it, and then when you delete an object, it tells you what's been freed up. In addition, it runs a thread during this, so it samples how much memory is used in an envelope during the calculation. So for example, when you've got 4 arrays here, you've got 3 you're using, and a 4th one is used for the result, a 5th is generated as a temporary that's hidden. So that adds another 1/5 of the memory allocation during the course of that command. Maybe you'd run out of RAM on your machine. So this is a nice way of just having a constant background understanding as to how much RAM is being used. Particularly useful if you work on one data set and then add a new data set that's 10 times larger and everything falls over. At least you get an understanding as you're going through it about where things might collapse. And then going one geeky step further on, I hooked in libperf. And so with libperf, I can see what the cache utilization is like. So for example, if we've got 2 arrays here, or a matrix and a vector, I operate on one in a Fortran addressed system, but it's a C-based addressing. That's unfriendly on the cache, at which point we can see 211 microseconds per loop and 230,000 cache misses. But if we operate on it in a cache-friendly C-ordered layout, then we get 14 microseconds and 5,000 cache misses. So you can ask for the cache misses to understand and explain why things are running more slowly than you'd expect. And you could swap out the cache analysis and look for instructions run or instructions stored while waiting for data or any of the other perf results that are available. Probably only 3 of you really care about this level of detail, but it's really quite cool. And so that brings me almost to the end of my short talk. When I taught the other day on high performance, I totally forgot to mention that I have some flyers with me, so if anyone wants a flyer, please come and grab one. And I'll also plug the PyData London meetup that I co-run in London. Every month we've got 500 people on the group. We have 90 in a room talking about data science-related topics in Shoreditch, free pizza, free beer. We move in a couple of months to a larger venue with 180 of us in a room. So if you want to come and get involved in that community, please just find us on meetup.com. Thank you very much.
Okay, so I want to sort of raise some awareness for a library that I've been working on, which sort of grew out of the frustration that a lot of libraries that need to read or write images tend to roll their own implementation, like Matplotlib and scikit-image have their own functionality for that. So I took some code which was written by Zachary Pincus and then incorporated in scikit-image, and I took it out again basically and started well, cleaning it up and expanding on it. Basically it's pure Python, so the idea is to make it very easy to install. So because yeah, it would be a dependency if you were to use it in another library, but it should be an easy dependency. It's so it's pure Python cross-platform, and it has a sort of plug-in architecture. So the core of image.io is quite small actually, and it sort of exposes 2 APIs. One is a public API, which is sort of on the left-hand side, and this is all there is. So you have imread for reading images, mimread for reading series of images, then full read for reading volumes, etc. And you have a matching set for writing data. Then there's a read and a save function, which gives you a reader and a writer object, which gives you some more fine-grained controls over reading and writing. For instance, to stream data. And there's a function to get help on a certain format. On the other side, there's like a developer plugin for people who are writing plugins. Basically, you implement a format class, a reader class, and a writer class, and you have some things that you can use. So you can ask for a file object, or you say, I want a file name to do the reading. And then you register the format using image.formats.add format. So you can actually implement formats for image.io without having the actual code in image.io itself. The thing in between, so the core makes sure that the two of them, the two sides work together, and it actually takes care of a couple of nice things, such as you can read data from HTML or FTP, HTTP, I mean, and also read and write from and to zip files, for instance. And the plugins that you write do not have to care about that. It's all taken care of by the center section, so to speak. So we use free image library, which is C++ library. So we kind of ship the DLL along when you install it, and but that gives you like PNG, JPEG, and all the common image formats. But I've also implemented DICOM for those who are interested, animated GIF, and I have an experimental version for video reading and writing, including the webcam stuff that you saw in the talk earlier. Which is experimental, but soon to be released if I can find some time. So yeah, time is actually quite of a problem. So if you're interested in this, I could use some help.
So my name is Yury, and I've been the guy who given the profiling tutorial a while ago, and I want to advertise my PhD project that I've just brought to completion recently. So I'm in this neural network business, but we always claim we want to understand the brain. To that end, we need to understand the dynamics of neuronal networks, not the kind of networks that, for instance, Kyle was talking about, but the real spiking networks from biological neurons and with synaptic connectivity and so on and so forth. So the dynamics is basically the dynamics of single unit plus connectivity. So the dynamics of single units are more or less known. Therefore, we need connectivity desperately to really understand what's going on there. We can do this through experimental methods. Unfortunately, they are limited to a very small number of units. That could be anatomical methods or physiological. All are, unfortunately, quite limited in terms of how many units you can reconstruct. However, you can record the dynamics at large scale, and the idea is how to do this from spikes. So traditional approaches have been non-parametric, pairwise. I was not the first one who got this idea. Many attempts of over 50 years, it didn't work mostly. So I thought I would be the guy to do that right, finally. And the optimal solution would be to make a statistical model and then make a maximum likelihood estimation of it. And the parameters would be the connectivity metrics, but 10 to the power of 7 dimensions. And I wanted to, so this in itself is insane. In Python, this is pure madness. However, I used the amazing scientific Python stack, Python, Numpy, SciPy, Cython, MPI for Pi, importantly, NLOpt for nonlinear optimization. And with 2 years of work and lots of profiling, which is now obvious, I guess, why I've got into all that. I lost track of the speed up. Was at least 9 orders of magnitude by now. And so that's the final result. It works. In the middle, you have the dynamics, sample recording. On the left, it's a simulated network that I tested on, and on the right is the reconstruction. So it's 1,000 by 1,000 metrics. You can see it's quite similar. And then this also gives you a dynamical model. So now you can plug these parameters into the model back again and simulate it, for example, perform virtual experiments and predict the behavior. And these are, again, an illustration. You can see that the original network and the reconstructed one behaves the same way when simulated. So that's submitted now under review in PLOS Bio. So it's coming to the nearest PLOS Bio website to you very soon. And I guess that's it. So I'll be here. If you're interested, talk to me. Thanks.
Hi, I'm Ralph. I want to talk to you about GNOME Focus. And GNOME Focus is a foundation that many of you have probably heard of, but are maybe quite unsure about what it does exactly. So it's a US-based charity with as goal to help improve the accessibility of open science and computational tools for open science. Right now I'm one of the people on the board of GNOME Focus, together with 8 others that are not here, unfortunately. What we do in practice is shown on the front page of this website. So a big part of it is PyData organization. That's done by our only full-time administrator for a lot of what the actual day-to-day organizing of PyData. And the reason to do that is that if it makes any money, that flows back into GNOME Focus, and then it benefits either educational programs or some of the projects that we try to support. Other initiatives are the John Hunter Technical Fellowship, which is a fellowship that is between 3 and 18 months. It's awarded once a year to a senior PhD or postdoc. To work on something important in the tool stack. Furthermore, women in technology, there have been several bootcamps by now in collaboration with Software Carpentry, specifically to get women, and it's usually run at the side of a scientific conference, in order to get more women interested in contributing to open science. Then the biggest part of this thing is projects. So what we do for projects is not directly related to code most of the time. But besides code, there's a lot that goes on in a project. Things that typically have to do with either money or with legal issues. And legal issues may also come back to money. So a lot of you will have seen this. There was a trademark foundation where a company tried to claim the name of Python, which would have been very inconvenient. So in order to do that, you need trademark protection. You also need to store your domain names and host servers and a whole bunch of stuff that you may want a legal entity for. A lot of projects are not legal entities. Projects like Numpy and SciPy, for example, they're just repositories on GitHub plus a mailing list and a bunch of developers. Well, those cannot own a trademark. So this is where GNOME Focus comes in. So if you have a project like that and you need help, GNOME Focus can help you. So I mentioned core projects, and I'm out of time. Please come to talk to me afterwards if you're interested.
Does this one work? Yeah. Cool. So the land registry, which actually has every single property transaction that has been made in the UK since 1995 in one massive CSV file that you can download and parse, and it's right there. So some really simple things that you can do with Python, like, you know, you can plot the average transaction value for a house in various different areas of London, or you can pull out, you know, every single transaction on a particular block of flats and plot them over time. I have made some really, really ugly scripts that do that if you wanted to play with this stuff, but actually there's a lot of data that's online, and there was some fuss recently about how the land registry was going to be privatized, but actually this is a really good public resource, so we should be aware of it and we should use the data that's there. And that's it.
Good afternoon, everyone. I'm Tracy Miranda, and this is actually my first EuroSciPy, and I have to say it has been terrific, or I think I have to actually say it has been Pi-terrific. But I come here from the Eclipse world, and I wanted to just share with you the Eclipse Science Working Group. So how many people have heard about Eclipse? Yeah? Okay, so quite a few of you. So Eclipse is probably best known for its IDEs like Java and PyDev, but it's much more than that. And the Eclipse Foundation very recently created a science working group. And the idea behind that is, again, under this idea of sustainable software, to get companies together to work on reusable software components and components that are well tested, well understood, and well documented. And how it really came about is that we had these two big companies, Diamond Light Source, who I work with, and they had the synchrotron based in Oxfordshire, and Oak Ridge National Labs, which is the big research center, which is in Tennessee. And both those companies had Eclipse-based workbenches. So Oak Ridge has one which is for modeling and simulation of nuclear reactors, and Diamond has a plotting workbench, which includes things like IPython and lots of workflows. So the idea behind it is to get together, well, those projects are already open source, so they want to make them available to everybody. They want to make the APIs usable in a way that they can be used for different disciplines. And so, yeah, there's lots of other companies. Future Coders, the little blue logo, that's me, that's my consulting company. So we do Eclipse. And yeah, I think it will be a very powerful group. I mean, if you just go by supercomputing power, it's really powerful already. And yeah, we're looking to just make more sustainable software. So if you're interested in that, have a look at the website, join the mailing lists, and get involved with the discussions. See if it's for you, or just come and talk to me. Thanks.
Okay, let's see if the screen works. It does. All right. How many people here use PyFlakes or something like this? Well, I guess I can just go and sit back. I mean, that's pretty good. That's pretty good. For those who don't, the very small minority, you're doing it wrong. The reason I'm giving this lightning talk is that I had the impression by looking over people's shoulder that people were not, but I got it wrong. Okay, for those who are not using PyFlakes, typically your workflow or my workflow when I'm not using PyFlakes looks like this. I run something, and then after an hour of computation, it crashes because I had made a typo somewhere. And if I use modern computing tools like pathos. I can run something like this on 20,000 nodes and get this after 20 hours of computation. So obviously this is wrong. Therefore, you need to have some kind of static analysis that is able to tell you that you've done a typo there. And one of these tools is PyFlakes. So disclaimer, I've not contributed a single line of code to PyFlakes. So you can run it by simply running PyFlakes on the test.py. So I can do it here. So I run PyFlakes test.py. Yeah. And it says it's unhappy. So that's one way of using it. But the best way to use it, I find, is to integrate it in your editors. So I'm a VI guy. So that's what it looks like. If it's well integrated, let me blow up the fonts. Then it looks like spell checking. So immediately, as I type, I can see that I've made a typo. So very close cycles, and I can fix the typo. So depending on your editor, it depends. There are different ways of integrating it. We made a note in the SciPy lecture notes in the debugging section on how to integrate it. And one last remark, if I use import star, then obviously there is no way PyFlakes can see that I've made a typo here. So conclusion, don't use import star. Thank you.
My name is Miroslav. I'm with the Department of Informatics at the University of Sussex. I just wanted to quickly talk to you about what vector models of word meaning are, and just make a quick note about an interesting side effect I noticed when I was playing with these kits recently. So there's an image that failed to appear here, but the idea is basically that instead of trying to tackle the meaning of words, we'll just assign a vector to every word. And that lets us use 300 years of linear algebra, and it's all great because Numpy is all there already. And these dimensions roughly correspond to contexts that a word can appear in. And the good thing is you can do all of that for free, completely unsupervised from text. The only trick is you have to have lots of it, and that tends to get computationally quite intensive. I'm going to be showing you examples from Word2Vec, which is one of the recent instantiations of that family of models. And the reason why I chose that is that it's more or less the most popular thing at the moment by virtue of being, one, reasonably good, and two, more or less the first decent piece of software implementing vector space models. And the examples that I've got here are using GenSim, which is actually something that has been talked about before. So the input to a vector space model basically looks like this. It's just text, and you can get terabytes of it off the internet for free. Google is... the examples that I'm going to show you here are all done on about 200 million words, which is just 200 megs of text. Google is doing it on 200 billion these days, overnight, on a cluster of several thousand machines. Skipping over all the technical details and the code, what you'd get essentially after running that piece of code on the 200 megs of data is, first of all, a learning curve, or rather how much time it takes to train that. That's just as an example of how quickly Python runs these days when you put Python in. I'm able to run GenSim in about 200 seconds on all of the 200 megs. So that's basically no time at all. And the accuracy of the model, as measured by the Google evaluation task, which we're going to get to in a second, actually tends to improve as you throw more data in. So if I had another 3 minutes, maybe I could have doubled the amount of data I process. It scales linearly, I think. The problem with these things is evaluation, because it's always very hard to see what's out there and what the model is giving you. So for example, what Google does is they just say, king is to queen as man is to what? And they only consider the top result that the model returns, which according to them has to be queen. And let's just skip down here and see a few examples. Basically, Google's task is quite hard because they only take the top neighbor. So here's a few examples here. The most similar word to softball without... Ooh. Okay. Sorry, guys. I ran over on massively. But if you want to talk to me about this, I'll be right there. Thank you.
So I'm going to tell you about this thing. So what this is the basic equation behind dynamic mode decomposition, which is a kind of a recent algorithm in fluid mechanics. There's a recent paper on it out this year, which is about sparse dynamic mode decomposition. So you can think of it as a bit like a super general like Fourier transform, which you can apply to spatially distributed time series, or you could think of it as like an extension of PCA but on time series. So basically we're taking our initial data, which is a bit like the psi over there, and we're fitting it with a load of modes, which is the phi, indexed by I, and each mode oscillates at a fixed frequency. And those frequencies, those lambda i's, are complex. So the frequencies are both, so your modes both oscillate and also have a rate of either growth or of decay. What this allows you to do is to identify transient features in your flow and just to focus on like persistent, like oscillating structures in your spatially distributed data. So there was some Matlab code that came with the paper, but that wasn't very useful, so I translated it into Python. I made a module on GitHub. So here's an example. So say you had some data which looks like this. This is some data from a fluid. It's actually from it's basically velocity data spread over like height and actually that's time on the axis. But imagine it's like another spatial axis, and you have a load of these like through time. So you apply your DMD to this, and you're going to get out a load of modes. But one of the problems with all these modes is you don't have a way of selecting which the best ones are. Now in PCA you can select your modes by just looking at the variance. So you can select like the top few modes by their contribution to the variance. But high variance in a mode doesn't necessarily imply that it's dynamically important, and vice versa. If it's dynamically important, it won't necessarily have high variance. And so that's what sparse DMD does, is it finds a way of selecting a subset of the modes which optimally represents your data. So you get some modes which look like this. The first mode, as the same as in the PCA, is the mean, and then you have a load of other successive modes which are just like perturbations on top of that, which will have a fixed frequency associated with them. So at the moment, what I'm trying to do with this is make it as fast as the MATLAB one, because annoyingly it's a little bit slower. So one thing I'm doing, this all comes down to this like innermost loop, which is basically this. And I'm already calling like LAPAC directly, and avoiding a bit of overhead there. So the next thing I think I could do is maybe like Cythonize this, but I don't really know how to use LAPAC stuff from Cython. I'm not sure how to do that yet. And I'm using accelerated anaconda already. So that's what that's heading. Last thing, little plug. I also wrote this simple tool which turns markdown stuff, a markdown document into an IPython notebook. So you might find that useful. Cheers.
Hi, my name is Clyde. I'm a PhD student at Imperial College London, studying theoretical photochemistry, and I'm going to talk to you today about a project I've been hacking on, which is a graph-based alternative to the dashboard in IPython notebooks. And I've been involved with this because I have this problem, which is I really want to use an IPython notebook as my primary research notebook. When I try and do that, I have this problem, which is I end up with massive notebooks that are really unwieldy. And that's because when I have my scientific problems and I have a series of scientific steps I need to take, I find there's loads of little technical problems with each step. And so I end up having to investigate those and solve them, and then those solutions end up inside the notebook I'm dealing with, and it ends up really long and really slow and also really hard to understand. So in order to kind of structure this sensibly, I've been trying to take those small pieces and put them in other notebook files. But then my project becomes really hard to manage, and I don't know where everything's going. So in order to kind of make this sensible, I kind of tried to build this alternative view of the dashboard where you represent your IPython files as just nodes, and you connect them together with links. And so the way it's getting the links is there are just normal URL links in the markdown cells in those IPNV files, and it's just extracting those and pulling them out and creating this view. And then you can open them just by clicking on them as you would normally. I haven't yet implemented inheritance, but I know one of the IPython core devs has a GIST that lets you inherit from other notebooks. So I've got the inheritance piece working, but I want to make the arrow nodes that will allow you to have inheritance. And the other thing is I want to be able to share a portion of my notebook with other people if I want to. So I want to be able to select nodes, which I can't do with both hands. So Yeah, I can select a bunch of nodes and then archive them to a zip file and just send them to other people, and they'll be able to reconstruct my project or the piece of my project I want to share and run it. And yeah, that's it.
Hi, I'm Julian Taylor. I'm one of the Numpy developers since about 1.5 years, and I quickly wanted to present what is new in the new versions of Numpy 1.8 and 1.9. 1.9, we have released a release candidate a couple of days ago, and we want to release the final version next week. So do some testing now if you want to report bugs. Oops, that was too fast. So some statistics. We are quite a healthy project, about 1,000 commits per cycle and 500 merges. So as you see, it's mostly small things as the merge to commit ratio is quite low. So let's start with what's new. Something which is already in Numpy a while are generalized ufuncs, which are ufuncs which work on, instead of on scalars, on vectors. And now in Nump 1.8, our linear algebra wrappers now actually use these. You can use this to more efficiently work with smaller matrices which are stacked in one dimension. For example, here you can see the old way was just concatenate loop, and the new way you can just do directly. And it's quite a bit faster, you just give the Python iteration. Something also we new added in 1.8 is a more efficient way of computing rank statistics like the median. Using iterative intro select algorithm, which is linear in time instead of linear logarithmic. In 1.8, median uses it already. In 1.9, percentile now also uses it. Some other improvements to percentile are it now has an interpolation argument, which allows you to specify some methods to interpolate between the rank statistics. Currently we have linear, lower, higher, and choose also the middle. Oh yes, here you see the difference in performance. As you can see, the other one is 80 milliseconds, so it's 4 times faster for this size, and it gets better the larger your array is. The percentile median functions now also support generalized access arguments, so you can now specify to reduce along multiple accesses by just providing a tuple, and you can provide the keep limit argument to allow easy broadcasting with the original array. For example, this means that now the median has the same calling interface as the mean ufunc. In 1.8 and 1.9, we added a few functions to help out with working with arrays containing non-values, which are often used to represent missing values. So we have in 1.8 the non-mean, non-sum, non-var, non-standard deviation. 1.9 adds non-median and non-percentile. And we have lots and lots of performance improvements in, so that was it. Indexing is a lot faster.
Hello. Just so everybody knows, about a week ago or 2 weeks ago, we finally released a new version of Matplotlib. So we have 1.4 now available, so I encourage you to try it out. And there are many, many features in this new release, including the pretty undocumented MBAG backend. And so I wanted to give you an overview of the MBAG backend and what it can do. So what is it? By the name, hopefully you can infer that that's the IPython notebook, and it gives you interactive Matplotlib figures in a live IPython notebook environment. We've seen a couple of interactive figures in the notebook already this conference, but uniquely, I think maybe uniquely, this is not a JavaScript library. It's still using the power of Matplotlib, but sending over images to the notebook in real time. So with Matplotlib 1.4, just to use it, simply choose the NBAG backend like that, and then you can continue an import pipeline as you normally would. And so, yeah, no surprises. This is just Matplotlib, and up pops a figure. And this is a live figure, so you can go over there and you get the data cursor in the bottom right there, and you can pan and zoom as you'd expect with Matplotlib. And it all does what you expect. you can turn off the interactivity, and the image gets saved into the notebook file itself. So that all works. I've got a quick demo here of using the widget functionality. So this basically just does makes a figure and updates it with a function. And let's just turn on the interact. And as we can see, this is calling into Matplotlib. I can zoom in and do what you'd expect. Okay. This is just Matplotlib. It's just in the notebook. And in case you were still wondering, because no Matplotlib demo now would be complete with an XKCD, without an XKCD plot, it still all just works, right? So, there we are. Yeah, there's nothing special about this backend. It is using Matplotlib still. So here I'm just going to make a map using a library that's built on top of Matplotlib called CartoPy to draw maps. And basically you just make an axis, give it a projection, and jobs are good in, hopefully. And this is an interactive map. That's about it, really. I had another live demo which got data from the web, but that's no time. So there's still some bugs. User interface needs improving. All this stuff, and that's it. There's some Matplotlib stickers in the front. If anybody is interested in maybe doing a meetup in the southwest of the UK, please find me and come and talk to me. And that's my GitHub handle. Thank you.
I'm going to talk a bit about an automated cell coverage segmentation project. Some colleagues in the biology department at the UVA had some microscopy images to segment, and this was a manual process. They had to do an image J. So we started out with an image like that, and the cells are defined by the areas of light and shadow, and they wanted a segmentation much like that. That's what they had to do manually. It took about an hour per image, and it was very frustrating and boring once you've done several hundred of them. So I managed to produce a Python-based automated solution for them. I use these libraries, so to the various people who've built and contributed to these, thank you so much. The first step, you've got to turn the areas of light and shadow into density. I use the algorithm reference below, you can ask me later. So we start out with this, and we end up with something like that. But you still really can't just use thresholding, so you've got to go a bit further. And plus the fact they wanted the areas between the cells, not just the cells, just to make things more difficult. And there's a sort of overview picture. The next step was texture classification. It's a fairly standard algorithm. You get filter responses, you then cluster them, label the pixels according to the clusters, and then we ended up using a Gaussian weighted sliding window, and finally a linear SVM classifier. And we start out with this, and we end up with that where the red is the automated segmentation, and the green is the manual one. And so the results are good enough, and the biologists project that it will save them about 50 to 75% of the time with the remaining manual work. So in conclusion, scientific Python toolkits are awesome. And I'd quickly like to demonstrate one more thing. Most of us are used to source code looking something like that. However, I think we can do something a little bit different, and this is a quick version of a program that I developed a while ago, and it's running as an IPython front end. So if we execute this, we end up with our familiar Matplotlib plot. But however, the code is also slightly richer. So, for example. And so we get some mathematical typesetting built into the editor. But taking it further, what else can we do if we imagine code going beyond just text? Well, for instance, we could take this regular expression So here we end up with a visual representation. actually have code just literally represents as a table, just in the middle of the source code, where we can even just pick it up like an Excel spreadsheet, copy, duplicate new cells.
Hey, that's it, that's it.
It's the real visual stuff doesn't quite work in IPython yet, but it's called the Larch environment. I'm making it into an IPython front end. So thank you very much.